In this lecture, we are going to look at functions and try to write them as power series. So go back to the very beginning of our series, the geometric series. If we have the summation of all the xn, the powers of x, it is actually a geometric series with, well, x to the 0th power, which is 1, plus x squared plus dot 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 forever, right? So this is a geometric sequence with the leading term 1 over 1 minus the common ratio x, right? This is A, and R is x. So we have the sum upstairs. The summation of all the powers of x is 1 over 1 minus x. The series converge if the common ratio, which is, well, the absolute value of the common ratio, which is the absolute value of x here, is less than 1. That's the condition for the series to be convergent. Now, if we use this, well, formula, we can write the following function, 1 over 1 plus x squared, 1 plus x squared, as a power series. And then, as a power series, we are going to determine the interval of the convergence. So 1 over 1 plus x squared is 1 over 1 minus negative x squared, right? Because we are using the formula or the geometric series backward. You have 1 over 1 minus x, it becomes the sums of x to the nth power. So we need 1 over 1 minus something in x, which is the negative x squared. So that is, again, using the formula upstairs, we are having the sum from n to 0 to infinity. The x in the formula became our negative x squared. So negative x squared to the nth power. And if I rewrite the sign part and sort of the absolute value part, it will be negative 1 to the nth power, then x squared to the nth power, or x to n. Okay. Now, that's the power series representation. What is the R? What is the interval of convergence? Or before that, what is the radius of convergence? Well, you are having a power of x, so we can just work on the root of the nth term. The limit of nth root of xn, of course, absolute value, is the limit nth root of, when you take absolute value on the nth term, first you can drop the sign part, the sign factor, absolute value, give it 1. So nth root of just x to n, which is positive anyway, because x squared is positive. So you just have x squared. And it has nothing to do with n, so you can drop the n. And from the root test, we know that when x squared is less than 1, the series is convergent. But when x squared is less than 1, that's actually absolute value of x is less than 1, or negative 1, and the positive 1 are the two largest absolute value you could have, but not reaching because you don't have the word equal to. Okay, or you can also do the factoring and quadratic as a quadratic function, that's also okay. But anyway, convergent when x is between -1 and 1. Then on the boundary, when x equals -1 or 1, x squared is 1. So pretty much the series becomes sigma n from 0 to infinity -1 to the nth power times 1 to the nth power, which is sigma from 0 to infinity -1 to the nth power. The limit of the sequence is not going to 0. It's -1 and 1 and -1 and 1 forever, right? So let me still write it. The limit as n approaches infinity -1 to the nth power is not 0 because it's 1 or -1 alternating forever. So when x equals 1 or -1, the series is divergent. That means the interval of convergence is just -1 to 1. The endpoints are not included. Then we have the theorem in general. If f has a power series representation, which means f can be written as a power series at A, then the coefficients are given in the form with the formula Cn equals, this is the nth derivative, okay, nth derivative. So we are having the formula Cn equals the nth derivative of f evaluated at A over n factorial. We don't know if the series will converge at x value, but we know if it does converge, the coefficient has to be these ways, okay? And so pretty much we have the formula for the power series. And then any function peaking an A, you can write it as a series, right? As long as the function is differentiable, you can work all its different derivatives out and you have this power series. So this power series, again, sigma of nth derivative of f evaluated at A over n factorial times x minus a to the nth power is called Taylor series. This is the Taylor series of the function f at A. And a power series representation is also called a power series expansion. Okay, so you are looking for a power series to represent the function. And when you are getting the Taylor series at 0, that's where A equals 0 and the whole, when A equals 0, let me use red. When A equals 0, pretty much the whole term become x to the nth power. You are really having a polynomial of x with coefficients. So it's such a special case, it has a special name. Instead of calling it Taylor series at 0, we call it Maclaurin series. Okay, so Maclaurin series means A equals 0. Now finally, if you have a finite series, which means it doesn't go all the way to x, xn doesn't go to infinity. You have maybe up to x to the 10th power, maybe you have x minus 2 to the 20th power, that's it. But as long as it's a finite series, which means this number doesn't go to infinity, then it converges for all x's, which means r, the radius of convergence, is infinity. Okay, for infinite series, we don't know if you can compute a Taylor series if it converges in, again, certain area, right? We have the three choices, either just at A, or you have a number, or it's infinity. We don't know for infinite series, but if it's a finite series, then r equals infinity for sure. With this formula, you don't need to use the trick, right, to write functions, because what if the function doesn't have the 1 minus 1 over whatever form? It was x, or the second question, negative x squared. But essentially, when we were using sort of the geometric series sum, the form has to be 1 over 1 minus something. In general, you have the Taylor coefficients, the CNs. You can work it out. Now let's see example 2. Find the Maclaurin series of the function f of x equals e to dx, and then find its radius of convergence. So we are going to work out a lot of terms of e to dx to see the pattern. And whenever you are working on the Taylor series or Maclaurin series, this will happen a lot. Okay, so instead of sort of work them randomly, you want to sort of like have a table thing. I don't know how big I'm going to write, so I'm not really drawing a table, but I sort of line them up in columns. So I start from my f of x, which is e to dx. Then Maclaurin means a equals 0. Then I need to evaluate f of 0, which is, I evaluate this function, right? It's e to the 0, which is 1. That's the first term. The zero's derivative, which means the function itself. Now, the first derivative, e to the x, taking derivative is still e to the x. So, f prime of 0 will again e to 0, which is 1. If I take second derivative, it will be the same thing, the same function. So, the second derivative will still be 1. I keep taking derivative, I keep getting e to the x as the derivatives. So, even if I reach the nth root, the nth derivative is still e to the x. Nth root of f at 0 will still be e to the 0th power, which is 1. Now go back to the Taylor series. We know that the Taylor series has the formula, let me write e to the x first, is summation n from 0 to infinity, the nth derivative of f at a over n factorial, then x minus a to the nth power for Taylor. And because we are doing a equals 0, it became sum n from 0 to infinity, f n of 0, n factorial, x to the nth power. And as you can see from here, by observing actually the nth root, the nth derivative of the nth derivative of f at 0 is just 1. So this will just be, if you write down the terms, it will be 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus dot 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 forever. And in particular, the nth term will look like 1. Any derivative of f at 0 is 1 over n factorial, then x to the nth power. That's the power series we are having, the Taylor series, or Maclaurin series, sorry. Okay, so that's our first thing, the Maclaurin series. Then it's radius. I guess I have n factorial, I'll work with the ratio test. And the limit as n approaches infinity, absolute value an plus 1 over an will be the limit as n approaches infinity. An plus 1 will be xn plus 1 over n plus 1 factorial over the nth term will be xn over n factorial. Then I flip it, xn plus 1 over n plus 1 factorial times n factorial over x to the nth power, and I cancel them, it will be just an x, and I cancel them, it will be n plus 1 on the denominator. So this gives me limit n approaches infinity x over n plus 1 inside absolute value. Well, So I can pull out absolute value of x out, limit n approaches infinity 1 over n plus 1. No matter what x is, the limit of 1 over n plus 1 goes to 0. So this is just absolute value of x times 0, which is 0 no matter what. That is less than 1. So our radius of convergence will be infinity by the ratio test. And I didn't ask, but the interval will be negative infinity to infinity. The question asked the radius. So there we go. From here, we know that e to the x converges to, well, it's equal to the series, which means for any x, the series convergent. In particular, since the series is convergent, the limit of x, the limit as n approaches infinity equals 0, which means for all the x's, doesn't matter what x's are, okay? The limit of any power, the limit of nth power of any number over n factorial is 0. So which means you have the limit n approaches infinity 3 to the nth power over n factorial, that would be 0. And also, if you have alternate, say negative 2 n over n factorial, that's also 0. So pretty much exponential goes not as fast as n factorial. Okay, that's example 2, but that's sort of belong to my remark. Okay. Next example, we are looking for the Maclaurin series of sine x. And same thing, we are looking for not only the series but also the radius. So f of x is sine x. And plug in, again, Maclaurin means a equals 0. F of 0 is sine, well, let me move a little bit back. I'm worried I don't have enough room. This will be sine 0, which is still 0. Then taking derivative, sine becomes cosine. So the derivative of f at 0 would be cosine 0, and that's 1. Now, second derivative, you are taking derivative of cosine x, which will be negative sine x. So the double derivative will be negative sine 0, which is still 0. Now triple, you are taking one more derivative on top of sine. You bring down the negative sign, give you cosine taking derivative. So the triple will be negative cosine 0, which is negative 1. Bear with me, we're almost there. The fourth time, negative times cosine taking derivative is negative sine. So negative sine, which is just sine x that we started with. So the fourth derivative of f at 0 would be sine 0, which is 1. Then you can imagine, you go back here, right? The same thing. So the next time it will be cosine x, then negative sine x, negative cosine x as a cycle, going back and forth again and again and again. So let me take those away because they are sort of ugly. Okay. Then our sine x, if you look at the beginning terms, 0 doesn't really do anything. So the first term is 0. Then the second term will be 1 over the first derivative, which means it's 1 factorial n factorial and nth power x. Then second is 0. We pass that term again, so because if you are going to bring it in, it will be 0. And then 2 factorial 2 squared, x squared. Then the third, you're having minus 1 over 3 factorial x third. So next term is gone. Oh, sorry, this is 0. Then you will have 1, 0, negative 1, right? So the fifth term will be plus again 1 over 5 factorial x to the fifth, dot, 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 forever. So actually we are only having, I don't need this is 0. I'm having only the odd powers of x, which means I'm really summing up the powers of, well, 1 is the first, so the powers are 2n plus 1. And look at the coefficients, they all have the numerator 1, but the sign is alternating, so I want starting with positive, negative 1 to the nth power, that's positive. I have 1 on the numerator times 1 over the denominator. I'm having 1 factorial, the same as the exponent, so 2n plus 1 factorial. Okay, or sigma n from 0 to infinity, negative 1 to the nth power over 2n plus 1 factorial, then x 2n plus 1, sort of coefficient and the power. So that's our Maclaurin series. And again, we have factorial. Well, you have factorial because of the Taylor, coefficients. They involve factorial. So most of the cases you will have factorial anyway. And then when you are computing the limit, ratio will be a good way. So again, I'll do the ratio. N approaches infinity, an plus 1 over an will be the limit. Notice that although we get our power series from the Taylor formula, but actually when you rewrite it, you don't have x to the nth power everywhere. So the nth term is not really the nth term that come from the derivative. Like, it's not the nth derivative. You know what I'm saying? So here I'm having the limit. I'm looking at this new series that I wrote down. So the nth term will be the absolute value. I'm not really including the sign. N plus 1 will be x to n plus 2 for n plus 1, then plus the 1 over, again, 2n plus 2, then plus the 1 factorial, then over x 2n plus 1, 2n plus 1 factorial, then absolute value. Sorry, that's a mess. So this will be the limit as n approaches infinity. I'll write the flip version. X 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over x to 2n plus 1. Same thing, the factorials cancel each other and the powers cancels each other. So I have x squared on top and I have 2n plus 3 and 2n plus 2 on the denominator. Then x doesn't really matter. I pull out x squared and I'm still having the limit 1 over 2n plus 3, 2n plus 2. As n approaches infinity, the denominator goes to infinity, the limit of the whole thing goes to 0. So I'm having absolute value of x squared times 0, which is 0. And what matters is less than 1. So again, the interval is infinity, negative infinity to positive infinity, but the radius of the convergence would be just infinity. Okay, so in this lecture, I do want you to write out a bunch of terms of the beginning of the Taylor series or Maclaurin series to observe the pattern so that you can write the general form of the pattern, because you need the general form to have an an to work on the radius of convergence. Maybe you do ratio test, maybe you do root test, depending on the form, but you will need a general term of an. Okay. Alright, now you can pause the video and try practice number 1 and number 2. The last thing for today is another theorem, a bunch of theorems. Pretty much what it says is if you have a power series that is convergent, for some radius r, then on the interval that the series is convergent, you can take derivative, or you can do antiderivative it will just be the sum. You are just summing up the derivative term by term, or summing up the antiderivative term by term. Of course, that will be up to a constant c. And the derivative of the function or the antiderivative of the function with their power series form will still converge with the same r. Maybe they can converge more, but they will have the same, on the same interval, they will be convergent for sure. And for the practice, although if you are watching the video, you haven't done it yet, but in the practice, I ask you to work out the Maclaurin series for cosine x, because I want you to observe what you have. So your sine x, we already did it in our example 3. Right? Sine x is the sum of -1 to the nth power over 2n plus 1 factorial x to n plus 1. And when you are doing your practice number 1, you are having the cosine x is the sum, well, n from 0 to infinity, the same -1 to the nth power 2n in parentheses factorial x to n. Because here I gave you these two questions to work out, because I want you to see the the connection. If you take derivative of sine, you should get cosine, right? But in particular, if you take derivative of sine x, by the theorem, you know that you can take the derivative term by term. It will be -1 to the nth power 2n plus 1 factorial x to n plus 1 derivative. Then you do the sum instead of doing the derivative this way, okay? And that is derivative with respect to x. So n doesn't matter. You are still having the same -1 to the nth power over 2n plus 1 factorial, because that's only involving n. But you are going to differentiate x to n plus 1. 2n plus 1, the coefficient, then you lower the power by 1, which will be 2n. Then the 2n plus 1 factorial and 2n plus 1 cancels each other. You will have only 2n factorial x to n, and that's exactly what it is for cosine x. So this is cosine x. Similarly, if you put cosine x in the antiderivative, you can just put a summation. You are doing the antiderivative of each of the terms, x to n dx. Then coefficient doesn't matter. The -1 to the nth power 2n factorial, that's the coefficient. Now antiderivative of 2n, you add the power by 1, then you flip the exponent, and the whole thing is up to a constant, so you plus c. And that gives you 2n plus 1 factorial. So you are getting sigma -1 to the nth power 2n plus 1 factorial x to n plus 1 plus c. And this is sine x. Okay, so you can see, actually, when you are having a power series representing the function, you can find its antiderivative or its derivative by just differentiating the series, which are polynomials. So derivative and antiderivative will be so easy, and then the new series that you get, the new summation, will still converge on same x values. Okay, that's what this theorem is really telling you. Instead of working on the original function, if you happen to have a Taylor or Maclaurin series that is converging, which means you are in the interval of convergence, instead of working on the original function, you can just work on the series term by term, which are, again, a bunch of polynomials. Okay, that's it for today.